The topic of this lecture will be the epoxidation of alkenes. An epoxide is a three-membered ring containing oxygen. As you can imagine, a three-membered ring containing oxygen is very reactive, and we will, later in the semester, talk about the reactions of epoxides, but first we're going to talk about how to synthesize them. To synthesize an epoxide from an alkene, we use something called a peroxy acid, or a per acid. Remember that a carboxylic acid has the general formula RCO2H. A peroxy acid or a per acid has a peroxide within the carboxylic acid functionality. The most commonly used peroxy acid is called M-chloroperoxybenzoic acid, and its structure looks like this. M-chloroperoxybenzoic acid is often abbreviated MCPBA. MCPBA is a popular peroxy acid because the per acid is soluble in most organic solvents, but the carboxylic acid that's formed as a product is insoluble and can easily be purified away. Now let's look at the reaction of a peroxy acid with an alkene to synthesize an epoxide. If we treat an alkene with a peroxy acid, we will get the epoxide product and the byproduct of the peroxy acid, which is the carboxylic acid. The mechanism to form the epoxide is a concerted mechanism. This has important stereochemistry consequences that we'll look at in a moment. But first, let's look at that mechanism. First, let's redraw the alkene and the peroxy acid in order to make it easier to show how the epoxide is formed. It is the terminal oxygen of the peroxy acid that adds to the alkene. So I've redrawn the peroxy acid so that terminal oxygen is closest to the alkene. The mechanism involves several arrows, but remember that because this is concerted, it happens in one step, and all of these electron movements are happening at the same time. You can, however, reason through them sequentially to help you remember which electrons move where. So just like other reactions we've looked at, we will start our arrows with the pi bond of the alkene, which acts as the nucleophile. The pi bond attacks the terminal oxygen. This oxygen can't have more than 8 electrons, and so the bond to the other oxygen, which is the most reactive bond in the peroxy acid, moves to form a pi bond to the carbon of the peroxy acid. That carbon can't have more than 8 electrons, and so the carbonyl of the peroxy acid abstracts the proton from the other end of the peroxy acid. And finally, the electrons from that proton, which can't have more than one bond, then attack back the alkene to form the epoxide. Now let's look at the transition state that shows all of these bonds that are being broken and made at the same time. The carbon-carbon double bond is breaking. The carbon-oxygen bond is forming to make the epoxide. The oxygen-oxygen peroxy bond is breaking. The pi bond between the oxygen and the carbon is forming. The pi bond between the carbon and the other oxygen is breaking. The bond between oxygen and hydrogen is forming. And the bond between the hydrogen and the oxygen of the epoxy is breaking. So all of these bonds are breaking and forming at the same time, and they produce the epoxide and the carboxylic acid byproduct. Notice that the oxygen that was the carbonyl is now going to be the oxygen that contains the proton in the product, and the oxygen that was part of the peroxy acid is now the carbonyl oxygen in the carboxylic acid product. Now let's look at an example reaction. If we treat this alkene with a peroxy acid, we will get the following epoxide product. Now let's look at the mechanism. Again, I've redrawn the peroxy acid to make it easier to draw the mechanistic arrows to show formation of the epoxide. In the first step, the alkene attacks the terminal oxygen of the peroxy acid. That breaks the peroxy bond, forming a pi bond to carbon, which breaks the other carbonyl pi bond, which protonates. The electrons that bonded that hydrogen to the terminal oxygen of the peroxy acid then attack the other carbon of the alkene. This forms a transition state that looks like this, where the carbon-carbon double bond is breaking. The epoxide bonds from carbon to oxygen are forming. The peroxy acid bond is breaking. The carbonyl pi bond is forming. This carbonyl pi bond is breaking. That oxygen-hydrogen bond is forming, and that hydrogen-oxygen bond is breaking. This forms the epoxide product shown above. Again, remember that even though we can't draw all of these mechanistic arrows at the same time, all of these bond breakings and makings are occurring at the same time. This is a concerted mechanism. What that means for the stereochemistry of epoxidation is that it is stereospecific, and we observe only syn addition of the epoxide. Let's look at an example. If we treat the trans isomer of this alkene with a peroxy acid, we get two products, both of them trans epoxides. If the epoxide adds from the front face of the alkene, we get this stereoisomer. If it adds to the back face of the pi bond, we get this stereoisomer. Both of these are trans epoxides, and these two are enantiomers. If instead we start with the cis alkene, we get the cis epoxide. Because of the symmetry in this molecule, there's a single stereoisomer formed from the cis alkene. Remember that the stereospecificity of this reaction comes from the fact that the mechanism is concerted. This is what is responsible for the fact that we see only syn addition of the epoxide.